Hello, welcome to the class on Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chatterjee. So in this class, we'll discuss about the antennas. We use mobile phones every day. Mobile phone also has an antenna. So now what happens to the mobile phone? When you speak over the mobile phone, the voice is captured by microphone and it's modulated and radiated into free space. And the device which will be radiating the signals into free space is the antenna. And again, this EM waves which has been radiated from the mobile phone is picked up by the base station antennas. So any kind of wireless communication needs antenna. So wireless communication cannot happen without antennas. You must have noticed that TV also has cables which we usually call as coaxial cables. So basically this coaxial cables or transmission line replace all the wires in the low frequency to the high frequency. When you work at the microwave frequency, all the wires will start radiating, so we cannot use wires. Instead of that, we use transmission lines like coaxial cables. So now the fields which were propagating inside the coaxial cables are called guided wave. So basically these fields are guided inside a guided wave structure. That's why it's called guided wave propagation. So now as soon as this guided wave reaches the antenna, it will be radiated into free space. So in a way, we can call antenna as a mode converter or mode transformer, in which you convert the guided wave field into radiated wave. So let us look at this example here. You have a transmitter, so fields are coming from the transmitting circuits. Usually have a source here. From the source, fields are coming through the transmission line, and the fields are in the form of guided wave now. As soon as it reaches the transmitting antenna, this guided wave will be converted into radiated wave in the free space. And again, what happens at the receiver is this radiated wave from the transmitting antenna will be captured by the receiving antenna, and it will be converted into guided wave. And this guided wave will propagate through the transmission line and goes to the receiver circuitry. And at the receiver, you will try to decode what message has been sent from the transmitter side. So in a way, antenna is a mode converter or mode transformer. It converts the guided wave to radiated wave or radiated wave to guided wave. Another very important property of antenna is that antenna can have directional radiation patterns. That means antenna can confine the power in one particular direction, and it can decide where to send the signals. Signals can be sent in one particular direction, or you may decide not to send signal in another direction. So that is dependent on one parameter called antenna radiation pattern. So this example will again explain what is directional radiation pattern of an antenna. You must have seen microwave tower. In the microwave tower, you must have also seen that there are big antennas fitted at the tower. So this is one transmitting antenna we're considering, which is fitted to a microwave tower 1. We also consider another microwave tower in a very far off distance, usually in terms of kilometers, and this tower is of very high height, so that this transmitting antenna and receiving antenna, they are in line of sight communication. There should not be any obstruction in between them. So now for this line of sight communication, antenna should actually direct powers along this line here. So for that, antenna should have a radiation pattern which should be highly directional. Even for transmitting antenna, even for the receiving antenna. So now if antenna is sending signal in any arbitrary direction like this, along this direction, this signal won't be able to reach this receiving antenna. So now the pattern of this antenna should be highly directed towards the receiving antenna. Similarly, this receiving antenna should also have a pattern which is highly directional, so that it can receive signals which has been transmitted from the transmitting antenna. Usually radiation pattern is a three-dimensional plot of the power radiated from the antenna. We'll try to define it properly in the following classes. So the previous example is for the directional antenna. Let's say you consider another example where you have a mobile communication. You have a mobile phone and you have a base station. So the communication between mobile phone and base station, for such kind of communication, the antenna should have patterns which should be able to transmit fields equally in all directions, or we should be able to receive fields equally from all directions. But such kind of antenna doesn't exist in nature, so we use approximation of isotropic antenna, which does not exist in the nature. We approximate it by omnidirectional antenna. So we should use omnidirectional antennas for the mobile station and base station, so that it can pick up signals from all directions, and it can also transmit signals in all directions. Because as you know that you carry mobile phones, and basically if you are in a motion, then you can be anywhere in the cell of the antenna, anywhere in the cell of the base station. So signal should be able to pick up signal. So mobile phone should be able to pick up signal from the base station antenna when you are in any part of the cell of the base station. So the most fundamental question is, when does a charge radiate? So we'll try to see what is the condition when a charge radiates electromagnetic waves. We'll consider three cases. First case is the simplest case, where you consider that charge is stationary. That means charge is not moving. So in that case, when charge is not moving, there is no current flow. If the current is not flowing, current is a source for magnetic field, so there won't be any magnetic field. So now you know that EM waves, electromagnetic waves, basically constitute electric field and magnetic fields. If magnetic field does not exist, we cannot have any radiation. So the first case we rule out. In the second case, we'll consider charge started moving, but now charge is moving with constant velocity. And we'll see that in this case also there won't be any radiation which would be able to produce electromagnetic waves. So in order to understand this clearly, let us consider a source as the origin, and you consider a giant sphere which is enclosing this source, and the radius of this giant sphere is r. So now how much is the area of a sphere? Area of a sphere is 4 pi r square. So now if this source is giving out power flow or Poynting vector as 1 by r square, if you multiply with the area per pi r square, you get the total radiated power. So Poynting vector is bearing as 1 by r square, and total radiated power would be Poynting vector into area is 4 pi r square. In that case, total radiated power for any r is always constant. Total radiated power for any r is constant. In that case, energy is not lost in the medium of propagation of the wave. So such kind of wave should be able to reach out far distance from the source. So the signature for radiation is irreversible flow of energy away from the source. So the radiated EM wave should be able to reach out to infinite space distance. So now, but in this case, when charge is starting to move with the constant velocity, in that case you can find out the electric field and magnetic field. Let's say if you use Coulomb's law, electric field will vary as 1 by r square. If you Biot-Savart's law, which is for magnetostatics, when you have a motion of the charge with constant velocity, you know that from Biot-Savart's law, magnetic field is varying as 1 by r square. So Poynting vector, instantaneous Poynting vector is E cross H star. E is the electric field, H is the magnetic field, and star is the complex conjugate. So now the amplitude of the Poynting vector will be varying as 1 by r square into 1 by r square, that is 1 by r to the power 4. So now the area of that giant sphere we have considered was 4 pi r square. When you multiply Poynting vector with the area, you get the total radiated power from that source at that distance r. So the total radiated power for any value of r is decreasing as 1 by r square. if the total radiated power is decreasing as 1 by r square, so this power will die out after some distance. So if the power die out after some distance, it won't be able to reach infinite distance. So the waves which has been radiated from the source won't be able to reach out to far off distance. That means you don't have proper radiation now. After some time, fields will die out. So let us consider the third case. In the third case, we'll consider a time varying current, or we'll also assume that there's acceleration or deceleration of charge. So you'll see that in this case there will be proper radiation which will be able to give us electromagnetic waves. So now we will consider one equation which is called basic radiation equation. In the basic radiation equation, what you have here is L di by dt. L is the length of a conductor and it is having a time varying current di by dt. Or here you consider another case where charge is moving with acceleration. dv by dt means we have acceleration. We have a charge which is moving with acceleration dv by dt. So this is called fundamental law of radiation. In the fundamental law of radiation, you should have a acceleration or deceleration of charge, or you should have a time varying current supplied to a conductor. So then you will have radiation which would be able to give us proper electromagnetic waves. So now you will see that we'll be discussing that in the next following classes, that such kind of conductor which is having acceleration or deceleration of charge, or conductor, small conductor which is supplied with time varying current, it should be able to give us an electric field which is varying as 1 by r. So if electric field and magnetic field is varying as 1 by r, Poynting vector will be varying as 1 by r square, and area of the giant sphere we have considered would be 4 pi r square. When you multiply the Poynting vector and the area of the sphere, you get the total radiated power from that source at that particular distance r, and in that case it will be always constant. So when you supply a conductor with time varying current, it should be able to give us a field which is varying as 1 by r, both electric field and magnetic field. And one more observation is that the direction of the field will not be along the radial direction. So these fields will be transversal to the radial direction. It will be perpendicular to the direction of power flow. Poynting vector will be directed radially outward, but these fields will be perpendicular to that. It will be in theta and phi directions. So two things: for radiation to happen, your field should be varying as 1 by r, and field should be transversal. It should be having components like theta and phi. And we'll see that in next class itself, when I supply a finitesimally small current carrying element, Hertz dipole, small current conductor of length dl, if I supply a time varying current of I naught exponential j omega t, we should be able to get fields which we have mentioned before, which vary as 1 by r and direction is transversal. Those kind of fields will be produced by the Hertz dipole, which is basically the basic building block or fundamental building block for any kind of antennas. That's the topic of discussion in the next class. And in one of the previous class we have also discussed that it's easier to find electric field and magnetic field from the potential functions. So we'll try to spend some time with the potential functions and try to derive its wave equation and solve it. So let us try to find out the wave equation for potential functions. You know divergence of B is 0 from the Maxwell equation. So now B can be expressed as curl of A. A is called the magnetic vector potential. So now you also have Maxwell curl equation. Curl of E is equal to minus dou V by dou T. You replace B is equal to curl of A. Then you can rewrite this equation here as curl of E plus dou A by dou T. So now this can be equated to another equation where you know that curl of negative of gradient of electric potential is equal to 0. So when you take curl of any gradient of a scalar function, it's always 0. So when you equate those two equations, you will get electric field as negative of gradient of electric potential minus dou I by dou t. So now in your electrostatics, you find electric field from the electric potential as negative gradient of the electric potential. But here you have one additional term, which is for the time varying fields minus dou A by dou t. So putting this in the Maxwell equations, divergence of E is equal to rho by epsilon, goes law for electric field. You replace electric field as minus dou A by dou t minus gradient of electric potential, and you simplify it. What you see is you have a term something like divergence of A. So now B is equal to curl of A. So that means once you know B, you know the curl of magnetic vector potential. So from the famous Helmholtz theorem for vectors, once you know the curl and divergence of vector, you know almost everything about that vector. So we already know curl of A is B, but we don't know divergence of A. So divergence of A is given by the Lorentz-Gauss condition. Lorentz-Gauss condition says that divergence of A is equal to minus mu epsilon dou V by dou t. So now if you plug that in the previous equation, you can cancel out terms. The final equation you have for the wave equation for the magnetic vector potential is like this: Laplacian of magnetic vector potential minus mu epsilon dou square A by dou t square is equal to minus mu j. J is the current density. So for the time harmonic fields, you can replace del square by del t square by minus omega square. In that case, the wave equation will become del square A plus omega square mu epsilon A is equal to minus mu j. So when people usually replace omega square mu epsilon by beta square, so wave equation will become del square A plus beta square A is equal to minus mu j. You can also get the wave equation for electric potential. For that, we'll use the another Maxwell curl equation. Curl of B is equal to mu j plus mu epsilon dou by dou t. So now if you replace B by curl of A, so curl of A, you use the vector identity, it becomes divergence of gradient of divergence of magnetic vector potential minus Laplacian of magnetic vector potential. So right hand side you have mu j plus mu epsilon, you replace E by minus dou A by dou t minus gradient of B, and you apply the Lorentz-Gauss condition. The wave equation you have for the electric potential is this: Laplacian of electric potential minus mu epsilon del square B by del t square is equal to minus rho by epsilon. But we'll try to solve the wave equation for the magnetic vector potential. So these are the wave equation for the magnetic vector potential and electric potential, but we'll try to solve the wave equation for the magnetic vector potential. For the time harmonic fields, I have already told you that wave equation simplifies to del square A Laplacian of A plus beta square A is equal to minus mu j. Beta is omega square root of mu epsilon. So if you want to solve this wave equation, there is a technique called Green's function technique. So in the Green's function technique, what do? You actually replace this right hand side. The right hand side here is minus mu j. Minus mu j. J is the source for the magnetic vector potential. Now you replace this source term here in the right hand side by a delta function and find out the solution of the wave equation. The solution you are getting is called Green's function, which is also called the impulse response of the system. So now once you have the impulse response of the system, which is called the Green's function, you basically do the convolution of Green's function with the right hand side of the wave equation. What do you have? Minus mu j. You do the convolution of Green's function, and this you will get the magnetic vector potential for any arbitrary current density Jr. So magnetic vector potential for any arbitrary current Jr is basically convolution of the Green's function and minus mu j. So here your prime coordinate denotes the source variable, unprime coordinates denote the observation points. So R is the position for the observation point, RDS is the position for the source. So let us try to analyze the similarity between this Green's function, this calculation of the magnetic vector potential from the Green's function, and the any current density J is very similar to what you do for LTI system. What do you do in LTI system? In a linear time invariant system, what do you do? Let's say you have the impulse response of the system as ht. For any arbitrary input xt, the output yt is basically convolution of xt and ht. So that is for the LTI system. So similar kind of things we are doing it here. So one major observation you can make is, for the LTI system, all the functions were time dependent. Y is time dependent, x is time dependent, x is time dependent. But here current density we are using is space dependent, Green's function is space dependent, and magnetic vector potential is also space dependent. So let us look at the analogy between LTI system and magnetic vector potential calculation. So input here for the LTI system is xt, for the magnetic vector potential calculation minus mu j, and impulse response of the system for LTI system is ht. Here is the Green's function. For LTI system, output is yt, and the final output we are calculating is magnetic vector potential. So let us try to solve the Green's function for the free space. So you assume an antenna which is located at the origin, and assume this is an isotropic antenna. For theoretical analysis, you can assume isotropic antennas is radiating equally in all directions. If the antenna is radiating equally in all directions, there won't be any variation of the fields with respect to theta and phi. So in that case, dg by d theta or dg by d phi would be equal to 0. So you remember that in the wave equation you have Laplacian of g plus beta square g is equal to delta r. Delta r is the source. When you have a delta source, the solution of the wave equation is the Green's function. But in the Laplacian expression, you have expressions variation of g with respect to theta and phi, but here they are not varying with respect to theta and phi. Fields are radiated equally in all directions. So dependence of the fields will be with respect to only r component, r variable or r coordinate. So Laplacian simply becomes 1 by r square del by del r square dg by dr, and you have plus beta square g is equal to delta r. This is the equation of the wave we are going to solve now. So now you just make a simple substitution, psi is equal to gr. Then the previous equation simply becomes del square psi by del r square plus beta square psi plus r delta r. So now what is the delta function? Delta function, delta r is 1 when r is equal to 0, and it is 0 for all other values of r not equal to 0. But now we are not interested in finding the fields at r is equal to 0. R is equal to 0, we have a source. At the source we don't want to find the fields. We usually find the fields slightly displaced from the source. So now r is no longer 0. R will be not equal to 0 in that case, because source is located at r is equal to 0. In that case, delta function will always be 0. So the right hand side here, r delta r will be always 0 for the fields which we want to find. So in that case, the previous equation simply reduced to del square by del r square psi plus beta square psi is equal to 0. And you can immediately see that such kind of equation is very familiar to you. It will have a solution of the form a exponential minus j beta r plus b exponential plus j beta r, where a and b are arbitrary constant. But look at this, exponential minus j beta r is a wave which is propagating radially outward from the source. But when you have exponential plus j beta r, this is a wave which is incoming towards the source, propagating along the negative r direction. But now source is at the origin and is radiating fields equally in all directions. In that case, we cannot have an incoming field towards the source. So the second term is 0. So in that case, the solution of psi is a exponential minus j beta r. So now psi was gr. So if I want to find g, it will be a exponential minus j beta r by r. This constant a can be easily found out It is given as one of the examples in the chapter 8 of the book I have written, Electromagnetic Field Theory. So if you are interested, you can check it there. We can even derive in the class. So when you derive this, you will find out that this constant here is minus 1 by 4 pi. So the Green's function will be, now it will become minus exponential j beta r by 4 pi r. So now Green's function for free space in our case is minus exponential minus j beta r by 4 pi. But usually people write it as exponential minus j beta r by 4 pi r. That is because when we do the derivation, see, basically we have replaced this right hand side by delta. No? So this right hand side has a minus sign here. So when I do convolution of Green's function, which was minus 1 by 4 pi r exponential j beta r with minus mu j, minus minus will cancel out. So in that case, the final expression would be like this. So now let us summarize what we have learned in this class. The first thing is that we've defined what is antenna. Antenna is a mode converter. It converts the guided wave to radiated waves and vice versa. Secondly, we have also observed that antenna can have directional patterns, and depending on what kind of applications we are looking into, antenna should have different radiation patterns. After that, we have tackled the most fundamental equation of radiation, basic law of radiation. There should be acceleration or deceleration of charge, or there should be a time varying current supplied to a conductor. In that case only we will have radiation, and for the radiation to reach out to far of distance, Poynting vector should be varying as 1 by r square. In that case, electric field and magnetic field has a variation as 1 by r. So when you supply this time varying current to a conductor, will have a field which is varying as 1 by r. And one more observation is that the direction of the field will be transversal to the direction of wave propagation, which is usually radially outward. In that case, electric field will have components in theta and phi, and its variation with respect to r will be 1 by r. So after that, we discuss about the wave equation for the potential functions, and it's easier to find fields from the potential functions, as you already know. So we try to solve the wave equation for the potential functions. In that, we have applied a technique which is called Green's function technique, and we have found out the Green's function for the free space. When I do convolution of Green's function for the free space with minus mu j, I get the magnetic vector potential. And that is all we have learned in this class. Thanks for your attention.